Hello, I'm Paul Beckwith. During the last glacial period, there were these abrupt warming transitions on Greenland as recorded in the ice cores. So temperatures over Greenland went up anywhere from 5 degrees Celsius to 16.5 degrees Celsius in the space of a decade or less. So the temperature would spike up and then it would dip back down over, 10 years, 20 years, it would have that rapid rise. And then over hundreds of years, it would fall back down. Even over 1,000 years, it would fall back down. And then it would terminate in this so-called Heinrich event, where ice was shed and huge amounts of ice were shed and cooled the whole region. So the question is are we undergoing a Dansgaard-Oeschger oscillation type situation here? I mean, we're getting rapid, tremendously high temperatures in the Arctic, and this warming is happening extremely fast. The Arctic is becoming a completely different place. So what I'm going to do is go into this paper that looks at these abrupt Dansgaard-Oeschger oscillations. It examines sediment cores in the Norwegian Sea, and it examines East Greenland ice core. So from the East Greenland ice core, it can get the temperatures over Greenland going back in time, and it can see that abrupt change. And from the sediment cores in the Norwegian Sea, it looks at biomarkers to determine the sea ice variation during these 4 Dansgaard-Oeschger events from 32,000 years ago to 41,000 years ago. So during the cold periods, they're called stadials, there was extensive sea ice cover. And then during the warmer interstadial times, when we had that rapid warming, there was a huge reduction of seasonal sea ice conditions in the region. And this rapid sea ice loss, for example, it caused a reinvigoration of deep convection in the Nordic Seas as opposed to stratified oceans. And it caused the abrupt warming transition in Greenland, that 5 to 16.5 degree temperature rise in Greenland in the matter of a decade or so. So, once the threshold was passed, it seems that the loss of sea ice can pass a threshold and then trigger these huge abrupt warmings in Greenland. And, we're already seeing that basically. If we take a yearly average, we're not getting anything like, 5 degrees to 16.5 degrees, over Greenland, although not 16.5, but probably approaching 5. So, it looks like a very similar thing is happening. So, we know when we lose Arctic sea ice completely, then it's no longer going to keep the Arctic cool. Arctic temperatures will skyrocket, and Greenland will start shedding a lot of ice. So maybe it'll create sort of a Heinrich-like event when it sheds all of this ice. So these are questions that I want to talk to you about here. So this is a paper called Rapid Reductions in Millennial Scale Variability in Nordic Seas Sea Ice Cover During Abrupt Glacial Climate Change. Okay, so here's the Dansgaard-Oeschger climate cycles during the last glacier mentioned. So they use sea ice proxy evidence from 2 Norwegian sea sediment cores and an East Greenland ice core to resolve and constrain sea ice variations during 4 Dansgaard-Oeschger events between 32 and 41 thousand years ago. Okay, so what they found is there was some threshold response between an extensive seasonal sea ice cover in the Nordic Seas during cold stadials and reduced seasonal sea ice conditions during warmer interstadials. Okay, and then there was deep convection of the Nordic Seas changed as the seas were warming, and the abrupt warming transitions over Greenland occurred. Okay, so I'll look at the key things here, the key figures. Here we go. The most striking feature of the Dansgaard-Oeschger events is an extremely abrupt climate transition that includes an atmospheric warming of 5 to 16.5 degrees over the Greenland ice sheet happening in just a few decades. Now, I've talked about this in previous videos, not for a while, but you know, these huge changes in less than a decade, can we see them in the Arctic? And you know, it appears that the answer is really looking to be like yes to that question. So here's Greenland, and here's Scandinavia. Here's the Norwegian Sea. So these diamonds are where the sea sediment, the seafloor sediment core samples were taken, and these are the ice core samples on Greenland. And these were these dots here they're using these biomarkers so they measured they looked at these biomarkers, and this is the particular biomarker here, and what you can see is the blue shading here, and this is a biomarker, and this was the extent of the September sea ice 1981 to 2010, and this is the March sea ice 81 to 2010. And these are the core top data. So the most recent data from the biomarkers shows high concentrations here. So this is matching nicely to where the sea ice coverage is. The September sea ice, March sea ice here. Okay, the blue shading areas. Okay, so we can use this biomarker as we go back in time to get an idea as to where the ice was. Okay, so that's the key thing from that figure. And then there's this is the Iceland. This is the ice cores on Greenland. The something called Del 18O. So isotopic analysis. Basically, we've got an increase of temperature with an increase of this factor. Okay, so now we're okay, so we get this. We get a rise in temperature here and a drop. Now this is going. Time is reversed here from the. Remember, I showed you this figure here. Okay, this is 50,000 years and 10,000 years. So time's going this way, and you get these oscillations. Big temperature rise, slower drop. Big temperature rise, slower drop. Big temperature rise. Okay, for the four main peaks and the smaller one here in the time scale that they're looking at, 31,000 to 42,000 years ago. But then when you go in this paper, you know, you have to go the other way. This is 42,000 years ago, 32,000 years ago. So we're coming this way. There's the first small peak. There's a big temperature rise here and a drop, big temperature rise, drop, big temperature rise, drop, and so on. So these are the different, so that's the temperature change over Greenland, and you can correlate it to the different biomarkers here. Okay, so these are a whole bunch of different types of biomarkers, and you can see spikes here where the temperature rise. So the biomarker and the biomarkers are related to the Arctic sea ice in those particular times. Okay, here's some more analysis where again on NGRIP. Okay, you have the spikes here from the oscillations. So very, very rapid rise, 10 years or so, and then a drop over, you know, say over. Well, this is a drop over a couple thousand years. This is a drop over, you know. So the cycle, these ones are shorter, right? This is 1,000 years between here and here, right? 34,000 years, 33,000 years. Okay, so the length of the cycle is varying. This one's very long here. This is a couple thousand years, maybe almost 2.5, 3,000 years to come back down after the spike. This one here, you know, much shorter, and these are very short. Okay, so there's lots of plots like this. This is showing some of the ice back in those conditions. Remember, this is in a glacial situation or a stadial, so the sea ice was much more extensive than it is today. This was the summer and fall sea ice boundary here, and this was the winter and sea ice extended down to here. So this is the seasonal ice and the perennial ice. And then in the interstadial, when the temperature rose, that large amount, then the summer sea ice melted back a lot further. Okay, so this was a world where there was a lot more ice. This is showing one of the cycles here. So from 36,500 years ago to 35,000 years, right? And a rapidly increasing temperature here. Okay, so there's lots of, so that's basically the gist of this. I'm not going to go into the details of all of these plots and things, but the key factor is that they had a method. They had a method using the sediment cores in the ocean and the ice cores. And the ice cores on Greenland gave us the temperature over time on Greenland. And we could see all of these spikes in temperature called the Dansgaard-Oeschger oscillations. And the sediment cores, they determined from biomarkers that were in the sediments, so dating the sediments, matching the sediment cores to the ice cores over this time period, where there were 4 or 5 sharp temperature spikes. They found out what the sea ice would look like before and after those spikes. And the sea ice was very important, of course. And what we have today with the rapid loss of Arctic sea ice, right? Everybody is sort of focused on the blue ocean event. When will we have a blue ocean event? When will the Arctic sea ice disappear for the first time in September? Okay, and then once it does in September, then that will condition the Arctic to be much warmer, so that the sea ice will take longer to form the next winter, and there'll be less ice forming in the winter. So eventually we'll have this blue ocean event where there's no Arctic sea ice, in September, and then. I've said many times that I think within a few years after that first blue ocean event, the duration of no ice will extend to a month, 2 months, 3 months, within a few years, and within a decade, no sea ice at all year round in the Arctic, and we'll have switched to a completely different regime. And so then what will happen? Well, from this paper, it gives us some clues, and what happened before. Although there was a much larger start to the there was much more ice to begin with. It shows that the rapid warming, the rapid loss of the sea ice caused a huge warming over Greenland. That 5 to 16.5 degrees, depending on which cycle you are in, and then that will cause tremendous amounts of ice to be lost from Greenland, and possibly cause a cooling in a similar fashion, temporary cooling in a similar fashion to what happened in the paleo records, and that will disrupt, of course, the AMOC, and it will wreak havoc on the weather patterns of the world. Like, we're already seeing tremendous extreme weather events, numbers of extreme weather events, increases in frequency, severity, and duration of extreme weather events because of the disruption of the jet stream. So, this paper gives some sort of clues as to what might happen and how long it might take. So anyway, thank you for listening, and I'll be doing lots of videos in the next in the next few weeks. So lots of topics. Thanks for listening.